the last lecture we looked at decision tree learning. Now, we will digress a little and look at a kind of learning which comes under statistical learning. So, specifically we will look at learning using neural networks. So, I will briefly introduce the structure and the basic definitions of a neural network, and we will see how we can use neural networks to learn different kinds of functions. So, a neural network consists of a set of nodes which are neurons connected by links. So, each of these nodes has very simple processing capability, and there are lots of them and they are connected by links. Each link has a numeric weight associated with it. Each unit has a set of input links from other units. It has a set of output links which goes into other units. It has a current activation level, which I will define shortly, and has an activation function to compute the activation level in the next time step. Right. Now, when we talk about such nodes and etc., for the time being we will assume that these are all done. This is just a model for computation. It is not that we actually have a processor which is doing all this kind of stuff. It is just that this is a model of computation that we are looking at, where we have a set of nodes having very limited computational capability, and we have these interconnections. So, a typical picture of a node is going to be like this. Can you see it clearly? Right. So, these are the set of inputs that we have. So, it is like AJ is an input to this particular node or neuron. There is a weight associated with every link. So, the weight from neuron J to neuron I is given as WJI. So, this is directed link from J to I, and it has weight WJI. Then we have a sigma function here which computes the total input that it receives from the other neurons. Right. I will define what is the total input. And then there is this activation function G, which is a function of the total input that the neuron I receives. Okay. It is some function of this, and that defines the activation AI of the neuron I, of this neuron I. Okay. And then this activation value is propagated through the output links to other neurons. Okay. The total weighted input is the sum of the input activations times their respective weights. Now, what does that mean? It means that if I have a neuron I, suppose this is our neuron I, right, and I have neuron J here, right, feeding into this. This has a weight of WJI. Then the input that I receives from J is the activation of J times WJI. This is the input that it receives from this. Okay. And if I want to compute the total input that I receives from all of its neighbors, preceding neighbors, then I sum this over J for all J which has which feed into this network, this node, right. And then in each step we compute the activation AI, which is a function of the total input. So, it is a function g of sigma of j wji aj. Is this clear? Now, this function can be of different types. It can be a threshold function, which says that that AI will be 1 if the total input exceeds some value. If the total input is more than 0.7, then AI will become 1. If the total input is less than 0.7, then AI will become 0. Right. So, we could have something like that, and so on. Now, let us see that how do we use a neural network like this for learning. So, this is a single layer network. I have one layer of input units here, these are the input units of the network, and I have one layer of output units of the network. Okay. These are nodes of the network. There is a wji, which is the weight of the link from ij to the output I, oi. If the output for an output unit is O and the correct output should be T, okay, then what do we mean by the correct output? So, what we are trying to do is we are trying to learn a function from the inputs to the outputs, right. So, again this structure of the neural network for a function which has 4 inputs and 3 outputs is like this, right. Now, what will happen is that we will be given a set of training data set, just like we had in the decision tree scenario. We will be given training sets. Those training sets will be valid input output pairs. So, it will be a set of cases where we are given I1, I2, I3, I4, and for a given value of I1, I2, I3, I4, what are the values of O1, O2 and O3. Right. We will be given several such cases, and the objective is to make this network learn that function, so that at the end of the training, if I repeat any example from that, if I give the inputs corresponding to any of the sample data sets, then the correct output should be displayed in the output. Also, if I give some inputs which was not there in the training set, then also correct output should be displayed. Now, again just like the previous case also, we can never be 100% sure whether it is giving the correct output for the others, but the objective is to make the neural network to learn the function, so that it is able to extrapolate also correct values for the input scenarios which were not given in the training set. So, obviously, we have to define an error term, and the objective will be to learn so that this error is minimized. So, if the output for an output unit is O, and remember that the output is actually a real valued stuff, because our activation values that we have are real valued, right. It can be real valued, it can be 0 and 1 also. If you use a threshold function, then the activation will be 0 or 1. If you use some other kind of function which gives real values as output, you can give that also, and then in that case O will be a real value. And if the correct output is T, then the error is given by T minus O. Now, the weight adjustment rule is Wj times Wj plus alpha Ij into ERR, right. Now, let us see what I will explain this in a moment. So, what we are trying to do is we are going to train the neural network in the following way. So, we will present it with some input value. Initially the weights are randomly assigned, they are all randomly assigned weights. I will give some input from the training set and then I will see what output it produces, right. Based on the output that it produces, I will compute the error, because in the training set the correct outputs are given, which is t, right. So, I will compute the error, and depending on the error I will readjust the weights on the inputs, right. Now, let us see in very crude terms that what would that mean. Suppose I will start by giving an example where the inputs are all booleans. So, let us say that I have these 3 inputs and these 2 outputs, right, and I have a complete connection. So, it represents a complete bipartite graph. Now, let us say that this is 1 2 3, this is 1 2. So, this is I1 I2 I3 and this is O1 O2. Now, I have given some value, let us say 0 1 1, right, and let us say that at this point of time this produces a value of 1, whereas, so this is our O and the value of O1, and actual value, which means the correct value T1 should have been 0. So, that means that what we need to do is, and let us say that the function that we are using here is a threshold function. So, it is a threshold function which says that if the total input is greater than 0.5, then this is going to be high, otherwise it is going to be low. So, that means that we want that the total input should be, for this case, should be below 0.5, so that the unit remains at 0, the correct value. Now, how can we do that? What we are going to do is, we are going to reduce the weights on the edges which connect to the 1 values. So, we will pick up these 2 edges and reduce their weight. What effect is that going to have? The total the input value will go down, because our input was sigma over j wji times aj, right. So, aj is 1 for these 2, and if we decrease wji, then the total input is going to go down, right. Okay. But at the same time, if we unilaterally decrease the weights here, then the total weight balance is going to change. So, what we are going to do is, we are going to reduce the weights on these and at the same time increase the weight on this, so that the total weight constitution remains fixed. It is just transferring weights from the ones which we want to reduce to the ones where we want to increase it, right. If we do that, then for this case we will move a little bit closer to the goal, right, and we repeat this case over all the training sets, with the hope that at the end of the training we will be able to correctly classify the samples, right, and be able to produce the right kinds of outputs. Now, as it turns out, I am going to come into the formal analysis in a moment, but as it turns out that these this kind of a single layer of neural network is able to learn only functions which are linearly separable. Now, let us understand what is linearly separable. Linearly separable functions are ones where you can have a plane in the Euclidean space which separates the positive cases from the negative cases, the yes answers from the no answers. For example, if you look at say an AND gate, right. Suppose we want to learn the AND function, right. So, this has two inputs I1 and I2, right. So, if you look at the two dimensional plane with this being I1 and this being I2, right, then if both are 0, then we have 0. So, this is a no answer. If one of them is 0, if I1 is 0, I2 is 1, then also it is a no answer. If both, if I2 is 0 and I1 is 1, then also it is a no answer. If both are 1, that is the only case where we have a yes answer. Now, this is linearly separable because I can have a plane which drives through this, right. Now, you might be wondering that what does this have to do with the learning here, right. I will come to that in a moment. Let us look at the OR function. If we have the OR function, then what we will have is this will be 0. So, I have I1, I2 here again, this will be 0 and these 3 will be 1, right. So, again this is linearly separable because we can have a plane like this, right. In contrast, let us look at the XOR function. So, for that this is going to be 0, this is 1, this is 1 and this is 0. Now, there is no way that we can drive a plane between the yes cases and no cases, right. Okay. So, this is a case which our single layer network will not be able to learn. It will not be able to learn the XOR function, right. Now, what has this got to do with our weight adjustment, etc.? Why can't it learn this? Why can it learn the other ones, right? So, let us simply look at the single layer network where if the total input is positive, we will switch on the unit. If the total input is negative, we will switch off the unit. So, activation will be 1 if the total input is positive, activation will be 0 if the total input is negative, right. So, then we have this sigma of j equal to 0 to n, where n is the set of inputs, wj xj, where xj is the input. If this is greater than 0, then the input switches on, otherwise it switches off, right. So, this is actually the equation w dot x is greater than 0, where w is the weight vector and x is the input vector, right. So, when this happens, then only we switch the unit on, right. Now, if you look at this function, this actually defines the hyperplane, right. This defines a hyperplane. See this x, okay. For 2 dimensions, this is going to be just a single line. If you have multiple dimensions, it will become a hyperplane, because each of this x can be k dimensional vector, right. So, this hyperplane is separating out, is acting as a threshold. Anything which is, if that is greater than 0 is on the other side, anything which is less than 0 is on this side, and so because that is the decision for switching the neuron on or off. So, that is the plane which separates the positive cases from the negative cases, right. Our objective is to learn the values of the weights, so that the weight vector that we construct along with the input vector will actually come to this plane. The weight vector will coincide with this weight vector which separates these two. That's intuitively the objective that we are trying to do. Okay. Let me quickly derive this particular equation for updating the rules. Then we will see some example cases of this learning and its applications also. So, first we define the error. So, error, for the error we are going to use the root mean squared error, RMS, which is the standard error that people wish to minimize between functions, right. You have studied, right, RMS error. So, what we are going to do is we are going to treat this as the error term. So, y minus this whole square, where perceptron is the network, is the simple network node that we talked about. It is a simple neural network node that we talked about. It is popularly called a perceptron. And right. Now, our objective is to update the weights in such a way that in each step this error will reduce. So, what we are going to do is we are going to do gradient descent. You remember gradient descent? What does gradient descent do? It has some objective function and we take steps so that that objective function gradually decreases, right. Of course, we have the problem of getting stuck in local minima. We have the same problem here also, but let us see how can we do gradient descent to minimize this error function. So, every step is going to reduce the error, right, and we want to do this monotonically. That is why gradient descent. We want to monotonically reduce the weights. So, remember that we are going to put different training sets and each time we are going to bring down the error further and further, right. So, to reduce this error, let us first see what we have as delta E over delta Wj. So, I want to see that what is the change in error with respect to a change in the weight that I receive from J. Okay. So, this is given as, this is given by ERR. Okay. What is ERR? It is the this is half ERR square, right. So, if I do this, then it is ERR times, see this 2.5 will get cancelled out because of the differential, this 2.5 will get cancelled out and I will have ERR times delta ERR by delta, right. So, I will have ERR times, now I substitute this out here, delta by delta Wj of G of y minus I think I missed a G here, it should have been, this should be the, there should be a G here. This is G of, G is the activation function of y minus, this is the total input, right, j equal to 0 to n Wj xj. No, the difference, the error is in terms of the output that we get, okay. So, this comes to minus of ERR into G dash IN, where IN is this total input times xj. Okay, and G dash is this derivative. See the other terms, see this besides xj it has other terms also, xi, the ones which are non j, right. Now, those terms are going to get eliminated because this is a partial differential, right. So, the only term that we will have out here is the one which corresponds to x j, right, and we will also have the derivative of the whole thing. No, could I make myself clear? No. This minus, no, this minus is getting propagated outside. This, because this is a constant, it gets eliminated, right. So, I have this term. Now, is this clear how we arrive at this? See, this is a constant, so it gets eliminated, and then this g, because this is a function, it becomes g dash of this whole thing, and then the partial differential moves inside, and when it moves inside, then everything which is non j gets eliminated, and I am just left with x j. Now, are you with me? Right. Now, this is the formula that tells us the weight updation rule. So, from this what we will get is, okay, so let me write down what we have obtained so far. We have obtained delta E. Yes. Huh? See, this is the see, this is the, I think this is, wait, yes, no, what is the confusion? Oh, the output is g of the total input. And this is the incorrect input that we are getting. This is the correct input that we should get, and this is the incorrect input that we have got, because our weights are not yet tuned. Yeah, I think what we are trying to do here is to minimize the error in the input, because if you are able to bring the total input to the correct value, then we will then the output will obviously be the correct one, right. Okay, just let me reflect on this a little more, and I will clarify it maybe in the next lecture, because we are going to revisit good part of this when we look at backpropagation learning. Okay, so for the time being, let us say that we have obtained that delta E by delta Wj is given by minus of ERR times G dash of in, where in is the total input into the perceptron, times xj, right. So, from this we set Wj to be Wj plus alpha into ERR into G dash in into xj, where alpha is called the learning rate. See, rather than adding this whole term, this whole error term into Wj, we are adding only a fraction of it. So, we are not just jumping into the same this thing, because in that would amount to something like quenching, but we do not want to do that. We just have to incrementally tune the weights, so that over all the samples that we have, we arrive at the at a set of steady state values of the weights, right. So, therefore, this alpha is called the learning rate, and we just add a fraction of this error into Wj, right. Is it clear? And we do this for each of the Wj. So, this was just computing delta E by delta Wj for one j, and we do it for each of the j's, so that we have updated the weights into of all the links that are feeding into this. Right. Right. Now, I will digress a little bit from this. We will come back to this analysis again when we look at two layer networks, where we will study a method called back propagation learning, where instead of learning in just two layer networks, we will learn in multiple layered networks. And the interesting thing will be, what are the internal nodes, what will they do. Here we have just the output layer and the input layer, and we are tuning the weights between the output and input layers, so that the output layers come closer to the desired values. The weights become closer to the desired values, so that it is able to give the proper output for all the training examples and others. Right. Now, let us look at a slightly different problem. We will look at the problem of recognizing text. So, let us say that we are given a matrix of dots. Okay. So, this is a matrix of dots that is given to us. And on this matrix we can have different letters by setting these to 1 and 0. For example, if we set this to 1, this to 1, then that gives us A, right. Similarly, you can have B, C, D, whatever. Now, what we want to do is that if somebody writes A slightly differently, maybe instead of writing it this way, it writes it that instead of lighting this dot, it lights this dot. So, it is slightly different. This one is off and this one is on. Right. So, we should be able to classify all those cases. So, I will train it with a set of different A, B, C's, D's, etc., and then it should be able to make out a slightly different perturbed A, it should be able to make out a slightly perturbed B, and so on, and be able to say that yes, this is still an A, this is still a B, and so on. Right. Now, how do we model this into a neural network framework? So, one option is that we create a neural network where these are the inputs. Each of these dot is an input which can take a value 0 or 1, and I have a set of output nodes, right, and each of these inputs will be feeding into those outputs, right. I will be receiving, these output nodes receive inputs from each of these units. So, I have again that 2-layer kind of complete network that we have, right. So, it is that complete bipartite graph that we have here as well, right. What we are going to do is, we are going to, so this is going to have at least 26, could have more also, at least 26. Then we are going to train this network so that whenever we have A, one of these glows, whenever we have B, some other one of these glows, whenever we have C, some third one glows, right, and the others remain off. Okay. Now, one way of doing this which was suggested was doing what is called competitive learning. Competitive learning sets up a competition between these nodes, and whichever is the winner is the one which will be declared as the value, right. So, which means that whenever we give A's, there should be one particular node which should become the winner for all A's, and one particular node should become the winner for all B's. Now, which one of these will classify the A's and which one of these will correspond to B, we still do not know. So, initially all weights are random, right. Now, this is how the learning will progress. Initially all weights are random. So, when I present it with the first A, one of these will win, right. Let us say that this one wins for A. Now, what we want is that in future whenever we present A, even with slight perturbations, this is the one which should win. So, what we will do is, we will strengthen this so that its activation value will further increase when we present an A. Now, how do we do that? When you have an A, then there are some, when you presented it with an A, then some of these units were 1. So, which means that there are some of these links which correspond to the 1s and some of the links which correspond to the 0s of the input. So, we will do that weight transferring. So, we will take a fraction of the weights from the 0 ones and transfer that weight and distribute it equally to the ones that we have here. Now, what we are going to have here is that the total weight will always be 1. So, for every unit, the total weight of the edges incident on that, the sum of the weight will be 1. So, whenever we redistribute the weights, the total weight will still remain 1, but now we have moved weight away from the 0 inputs to the links corresponding to the 1 inputs. So, next time when we give A, that activation of this, the total input to this will be more. So, it will stand a larger chance of winning, right. On the other hand, what do we do with the ones which had lost the competition? So, for the ones which lost the competition, we will do the same, but a much lesser fraction. For the winner, the fraction of weight that we transfer will be larger than compared to the losers. The losers will be for the losers we will take out weight from the 1 inputs and transfer it to the 0 inputs, but the fraction of weights that we transfer will be much lesser, right. Having done this weight adjustment, we then again present it with another sample and repeat the procedure. And the idea is that and our expectation is that eventually these nodes will start classifying some particular letter. So, there will be one which will always come up for A, one which will always come up for B, and one will always come up for C, and so on, right. But just like, so this is also gradient descent, this is also gradient descent. Why? Because if you take any particular node, it is being dragged on to something. What is it being dragged on to? So, if we one view of looking at this is that each of these is a vector, this is a vector, right, this is a Boolean vector, and it has so many different dimensions. So, if there are some 20 dots here, then this is a 20 dimensional vector. So, let us think of the 20 dimensional hyperplane. If you look at the 20 dimensional hyperplane, then in that plane each of these samples is a point, because every vector is a point in that 20 dimensional hyperplane. So, I have the A as one of the points in this hyperplane, right. So, just remember that this is just not a circle, it is actually a hyperplane, right, it is actually a hyperplane, and this is one point which corresponds to the A. Then similarly, we may have another point on the hyperplane that corresponds to B, and another plane which corresponds to P, right. The one which corresponds to R is going to be close to P, right, and so on. And where are our vectors here? Each of these vectors, the weight vectors that we have, they also correspond to points in this plane. So, I will have some vector here initially, say one is here, one is here, one is here, one is here. So, what is happening is that when I present an A, let us say that this fellow wins. So, the weight adjustment rule is moving it towards A, right, and for B, if this one wins, then this is going to move towards B, right. And also the weight adjustment rule is going to take to a much smaller extent the ones which are here to slightly away, right. So, as we were saying that the ones which are yes, now why do we do that? Why do we move them away? We move them away because of certain scenarios. So, this part is clear that the weight adjustment is actually taking it closer to these to the vectors that correspond to the actual things, and when you move it closer, if you give a slight perturbation of A, let us say A dash which is here, or even if A double dash which is here, then it is more likely that this fellow will win once it moves closer to here, So, you will have this vector will not only have learned the A that you presented, but also learned A's which are close to that, right. Now, that is the good thing about this. There can be some problematic situations for which we have the other kinds of rules. So, suppose we have a scenario where one of your, suppose we have A here and I have say B here, and incidentally it turns out that both of these are pretty close to this one, right. Now, what is happening is that every time this one wins, right. Okay, let me not this case, forget about this case. I have x b here, sorry, b here, and then I have A here and this is here and other ones here. And now see, the problem is that every time you present A, it is this one which is going to win and it is going to move slightly towards this direction, right. And every time you present B, it is this one only which is winning, because this is absolutely the opposite way. And if this one again wins, then that means that this is going to again be dragged on to this side. So, it is going to oscillate between these two, whereas there is another vector which is not being used at all. So, whenever you have a losing one, so whenever you present A, this one wins, this one loses, so you push this away slightly, then that is going to have the effect in the long term of moving this slowly around, so that at some point of time it is going to come pretty close to B.
Would B also push it away?
Yes, B is also going to push it away. So, if you have a scenario where you are presenting A and B alternately, then again you will have a bit of a problem. So you have to mix up your training in such a way that it eventually starts classifying, right. So the intuitive idea of moving it away is this: to move away those vectors which were not being used at all, which are not winning on any cases. If we can move them away slightly, then maybe somewhere down the line they will move close enough to someone else and actually start participating in the classification. Having vectors having outputs which are not winning in any case is not useful, right. So, we still, as you can still imagine, that there will be cases where we will get stuck in local minima, and you will have one vector which is moving around between two of them, right. But in many cases we will be able to do this, and if we put in more vectors, more outputs, then it is more likely that we will. Another option is that if you have a particular output which is not playing a role, you re-randomize the weights to that, so that it now moves into an entirely different place and maybe starts participating, right. So, this is one paradigm of learning that we have learned today. So, in the next class we will be talking about a learning algorithm called back propagation learning. In the last lecture we had started off with neural networks, and we had seen that how by using very simple processing units called neurons, we attempt to learn different kinds of functions. So, the model that we looked at in the last lecture was what is called a perceptron, and a perceptron is a single layer network where we have neurons which are simple processing units, and we had a set of input units feeding into the neuron. So, we had each neuron was like this, and we had actually a collection of other neurons also, and each of these other neurons would also receive inputs from the same set of input lines, right. So, this was the simple form of a single layer network that we had looked at in the last class, right. And then we wanted to see that how to compute the weight learning function. So, initially all the weights are randomized, and we want to learn the weight learning function, so that after we have learned the weights and we are presented with the inputs, the neuron outputs or the activation values of the neurons should have the correct output value, right. So, for example, one way of these neurons can have different kinds of functions that they can compute, of which one is where you compute the total input to the unit I as sigma wji, right, over all the inputs j, right, times the input that you receive from j. So, this was defined as the total input, right, and then we define the activation function as some g of this input, and that is the output that this neuron is going to have, right. And we saw that there can be different kinds of functions for g, of which the two most common ones are the sigmoid function, which looks like this, where the input changes gradually, or it could be a threshold function, which means that the moment you reach the threshold it will simply switch on. So, it is off, when you reach the threshold it switches on, right. Yes, these ones, they are the input units, they are the inputs to your neuron, right. So, a neural network will have several layers of neurons like this, and will have one layer at the bottom of input units, right.